So Rodrigo is also using immersed boundary method, and this time this is to do a pipe flow simulation, which is obviously a very interesting idea on a Cartesian mesh, and is looking in particular at heat transfer. So please, Rodrigo, we can see your screen, we can see you, so you have 15 minutes.
Do you hear me okay?
Yes.
Yes, okay. Thank you very much, Sylvain, for the introduction. Good afternoon, everyone, or good night, or good morning. For the next 15 minutes, I'll be presenting to you some of the main results we have obtained in nearly 3 years of research in pipe flow with XCompact 3D and also with Compact 3D. So I'll start with a brief presentation of the numerical methodology and the pipe flow configuration. After, I will describe this new technique that was recently developed, the viscous filtering, that was really, really important for the advancement of this work. And then I will move to the presentation of the latest results and numerical developments for the simulation of heat transfer in pipe flow that have been working on. The simplest one, to impose a mixed type boundary condition, which consists in the imposition of a Dirichlet boundary condition, simple. And then some new techniques that they have been working on to impose a Newman boundary condition in XCompact 3D, which allowed us to simulate an imposed flux and also conjugate heat transfer. So starting with the numerical methodology, starting with the numerical methodology, I will be brief here, as I think most part are familiar with the functionalities of XCompact 3D. We use 6th order schemes for the spatial discretization. For the time integration, use the 3rd order Adams-Bashford. For our DNS, as we perform it almost always in marginal resolution, we use some small amount of numerical dissipation for regularization. And this new technique, the viscous filtering, allows us to suppress the diffusive terms from our governing equations, so that any stability constraint related to diffusivity is strongly relaxed. We'll speak about it again ahead. And here our forcing terms here, our source terms, sorry, F2 and F theta they are source terms that are adjusted every time step in order to keep a constant flow rate and a constant bulk temperature for the temperature transport. For our pipe flow configuration, I will briefly present it here. We use a regular Cartesian mesh to discretize the 3 Cartesian directions. X and Y are the transverse directions, and Z is the streamwise one. When we use a Cartesian mesh like this to discretize a circular pipe geometry, we obtain an irregular distribution of our mesh nodes with respect to the wall. So some of these mesh nodes are found in a distance smaller than the mesh resolution itself, which means that for our statistics, when we project it from our Cartesian coordinates to the cylindrical ones, we can actually obtain information in a distance smaller than the mesh resolution, which is a major strength of our technique. Concerning the IBM, which represents the solid, we use also the reconstruction into the solid zone. We use the Lagrange polynomials of 5th order, and they are the Lag-Paul subroutines in XCompact 3D. Now, passing to the viscous filtering, it has been implemented in our version here. It's not still available. We are making the last tests, but it has been implemented in XCompact 3D, only for periodic boundary conditions, though. I want to present the principle of the viscous filtering here, but we have just published an article, and we published it this year. It's still free access for the next 30 days for those who are interested. So some of you might be familiar already with the principle of the ISVV implemented in XCompact 3D. Basically, we use a certain amount of numerical dissipation concentrated at small scales to regularize the solution, or even to substitute explicit subgrid scale modeling in the context of LES. This is done through the finite difference operator of second derivatives as it is implemented in XCompact 3D. Now, when it comes to a filter, what we see is that the deviation of the filter transfer function from 1 corresponds also to a numerical error that is introduced by the filtering procedure. This numerical error that is an artificial dissipation, can also be interpreted as a spectral viscosity, just like for the second derivatives. So as the filter is also a finite difference operator, we can design it to introduce a target dissipation or to mimic an SVV. So for example, here in the figure on the right, we have an exact match for the viscous kernel of our filter and the one for the second derivative. When you think of LES, when we use filters usually for the LES, we aim to remove all the scales at the cutoff wave number. So you want to have a transfer function equal 0 by setting our variable sigma equal 1. So when you do it, for example, we have here displayed this well-known filter of Lilly, which is widely used. Okay, when we use it and we see that in terms of numerical dissipation, it corresponds actually to an infinite value at the cutoff wave number, while being highly intrusive at large scales, and this is not very good. So this happens for any type of filter, no matter which one, if we aim to remove all the scales at the cutoff wave number. So when we use the viscous filter, designed as I presented in the previous slide, the filter operator, the filter application already bears the diffusive effect. That's why we can remove the diffusive terms from our governing equations. And what we have left, for example, for the velocity or the momentum equation, it's just an Euler equation. And in the paper that we have just published, this was the term we used to address these results, Euler plus filtering. I have provided you with some of the statistics here to exemplify the efficacy of the method. And since we apply the filter to represent the diffusion, the AB3 scheme is used only for the convective terms. Okay, and in this sense, it can be seen as an alternative to implicit time advancement for the diffusive terms. In our pipe configuration, for example, diffusivity has been always the most restrictive constraint for stability because of the IBM and those nodes that are found very close to the wall that I described before. So for us, the viscous filtering allowed us to obtain really significant reduction in the computational costs from 50 up to 95% of computational saving. We'll move now to our results concerning the heat transfer. We start with the mixed type boundary conditions, which consists in simply imposing a Dirichlet boundary condition. It is a fixed value at the wall, and this is done straightforwardly with the lag-pulse subroutine, so no extra numerical development was implied here. And I would like just to highlight that saving of 95% that I just mentioned, it was obtained for one of the simulations that we performed in this configuration. It is this one here. I show here some other temperature fluctuations for this case for a Prandtl number of 0.025, which is characteristic of liquid metals. In these conditions, the stability constraint linked to diffusivity is really, really restrictive. And for us, it was really a miraculous saving to perform the simulation and to develop this technique at the right and the good moment. I will pass now to the imposition of a Newman boundary condition. I would like just to highlight that this technique is still under development since last year. So I will be presenting only the principle here. We haven't published anything yet, and we are still working on that. So when we speak about the Newman boundary condition, we want to impose a derivative at the wall. And in our case, we don't impose the wall derivative exactly. Instead, we adjust the value, the temperature value at the wall in order to obtain the expected derivative. In other words, our Newman boundary condition is virtually ensured through the imposition of a Dirichlet boundary condition. We do it basically in 3 steps. The first step, we extrapolate the temperature value, the wall value, to obtain the expected derivative. And although we deal with a mesh arrangement, which is disconnected from the wall geometry, remember we use a regular Cartesian mesh to discretize a circular geometry. Although we deal with this disconnection, the technique developed is strictly 1D in order to be compatible with the MPI pencil structure of the code and of the reconstructions. And in step 2, we use this predicted value to perform our Lagrange polynomial reconstruction into the solid zone. In terms of numerical development, 2 new subroutines have been created to manage these reconstructions. So here are some of the statistics that we have already obtained. We have a good agreement in general. Only for the temperature fluctuations, we see a small difference close to the wall here. Like I said, we are still working on that. We have come to new ideas even this week, and we are still testing. So I think this can be further improved. And now for the conjugate heat transfer, when we speak about conjugate heat transfer, we are speaking about simulating at the same time the fluid temperature field and the solid temperature field. For the fluid field, we solve that conduction diffusion equation that I presented before, and for the solid field, we are going to solve a conduction equation. Numerically, these two equations, the one for the solid and the one for the fluid, are coupled at the interfaces through the thermal boundary conditions. So if you see here, for example, the figure on the right, for the fluid temperature field, it consists of imposing a Dirichlet boundary condition, a fixed value of the boundary. And for the solid temperature field, it consists of imposing a Neumann boundary condition, a flux. We use a weak coupling for these equations, which means that it's a non-iterative method, and in terms of the additional cost, it's minimized. So to manage the solid and the temperature, the solid and the fluid temperature fields, we use what we call a dual immersed boundary strategy. It has already been used to simulate channel flow successfully, and it's been used for the first time for a geometry that it's not connected to the mesh arrangement for the pipe flow. In this strategy, each field has its own physical and reconstruction domains. So if you see here, for example, the blue curve represents the fluid temperature field. For the fluid temperature field, the reconstruction domain is the solid zone. And for the solid temperature field, the reconstruction domain is the fluid zone. With this strategy, the spatial derivatives are computed independently for each one of the temperature fields, and the discontinuities are easily handled at the interface. I'd like to highlight here that the reconstruction for the solid in the external zone, the fluid external zone, is done through the periodicity. So the reconstruction that we see here on the right side reconnects to the one on the left side here. In terms of numerical development, 6 new subroutines were created. Should do this. And I finish my presentation with this fresh result. It's a visualization of the temperature fluctuations for sorry, it won't work like this. So like this, okay. It's a visualization of the temperature fluctuations for a low Reynolds number simulation. And we can see that we capture quite well the interaction between the fluid zone and the solid. The interface is here, and we don't see any spurious oscillations, which shows that the coupling seems to work quite fine. We have not looked at that statistics yet, because like I said, it's fresh, this result, we just obtained it. And also we don't have reference to compare for a conjugate heat transfer, but we are quite optimistic. So that's it. Thank you.
Thank you very much, Rodrigo. Very nice presentation. There is a question from Kai about the small discrepancy that you observed on the temperature variance at the wall. And he's asking about which formulation do you use? Yes, this one. Which formulation did you use for the convective term for the temperature equation?
For the convective term, we use the skew symmetric formulation.
Okay.
We have tested some others. We have tested the U gradu, so I know the term in French because I'm always reading it in French. We have tested some others, but mostly for the velocity
Okay.
to investigate the behavior. But for the temperature, we have not tried. It's very interesting. Thank you, Kaya. I will take a look on that.
Okay, cool. Thanks for your answer.
Stefano is asking, for the cylinder work, has the swap between X deer and Z deer as panwise, streamwise direction been tested? So just you confirm that your streamwise direction is Z.
Is Z. My streamwise direction is Z, yes.
Okay. And you didn't encounter any issues by switching from, I mean, usually we are streamwise in X. There was no particular issues by being streamwise in Z.
Okay, sorry. So here I presented, in the presentation, I put my streamwise direction as Z, but in the code, in XCompact 3D, I have adapted the streamwise direction as X.
Okay.
Okay, to be consistent. In Uncompact 3D, we used it in Y before, and we didn't have any problems.
Yeah.
I didn't encounter any problems.
Yeah. Very good, thank you. About the solid and fluid, you are using the same time step and same mesh resolution?
Yes, same time step and same mesh resolution.
Okay, so there's no issues with that. I mean, usually the time scales might be different in a solid or in a fluid.
Yes, we didn't encounter any problems. Like it's our first test. The method I finished preparing it last week, and we are performing the first test now, basically.
Very good. And one final question from Omar is, can you tell us, so you said that when you have points too close to the immersed boundary method walls of the cylinder, it's affecting the viscous stability.
Yes, this is a problem that we encountered since the beginning. Because of the irregular distribution of the mesh nodes, yes, it can affect the stability.
And I think Omar wants to know why.
So
if you can answer in 2 minutes, that would be amazing.
Yes, well, because these points are found very close to the wall, and because of our IBM, we cannot consider our mesh size of in the CFL condition to predict our time step. For example, we have to consider, theoretically, you have to consider these close nodes, but it's still not the closest ones. It's something that we don't understand very well, to be honest. We don't have this answer. I was speaking to Eric about that today. We are still trying to understand, but we know that the IBM is the responsible.
Okay. Well, thank you very much, Rodrigo, and good luck. I think you are close to finish your PhD, so
yes.
Good luck with that. Thank you very much.